Hello friends, welcome once again. Today we are going to discuss the topic of center of mass. So first of all we will discuss what is center of mass. Then the next important question is, before finding the center of mass of different bodies, why do we find the center of mass? What is the use of this? Then what is center of gravity and what is center of mass? What is the difference between them? Or what is the similarity? Then we will find the center of mass of different bodies, and these different bodies include the individual solid bodies. So we will define the center of mass of these bodies. We will find where is the mass actually is concentrated for these bodies. Like we have one dimensional or linear. Like we have a straight rod, the mass density of which is variable. If the mass density is constant, center of mass is at the geometrical center of the body. But the mass density is variable, that we will find. Then we have a bent wire bent in a semicircle, 1/4 of a circle, or in the form of an arc. Rod or bent wire, arc, etc. Then we will find this for two-dimensional bodies, which are also known as planar bodies. And this means we have a plate, like we have a circular plate, or we have a triangular lamina plate or lamina, or such bodies. Suppose I have a circle or a lamina, circular plate having uniform mass density, may also have non-uniform. Here we will consider uniform, and I take another circular portion out of this. This has been removed. So where is the center of mass of the remaining body? This we are going to discuss. Then we have solid bodies, that is three-dimensional, like a cone or a shell, etc. Hollow cone, solid cone, shell, etc. So these we will be finding. And then we have discrete bodies. First of this, discrete bodies. This continues. Suppose four bodies or four solids of different masses have been kept at four corners of a square. They are not joined to each other, or may be joined by massless rods and or three corners of a triangle, and we have to find the center of mass of them. These are called discrete bodies. And we have two body problem. Two bodies kept at a certain distance are not joined to each other, and we have to find the center of mass of these two bodies. It's called the two body problem. So these things we are going to discuss here. First of all, let us discuss what is a center of mass. COM, as we write it in brief abbreviation. So before doing this, I will explain you that if I have a plate, circular or any other type of plate, you take a plate, try to balance it on your finger. So what happens? Why you are able to balance this? This is the axis of this passing through its geometrical center, and I try to balance it on my finger here, putting my finger here. So I am applying a force. This is applying weight on my finger. As a result, the finger is applying the reaction. So weight is acting in downward direction, and the normal reaction is acting in upward direction. And in equilibrium, these two are equal. So there is no net force acting in the vertical direction. It means that this is not going to fall. If I put my finger here at this place, if you displace your finger in this direction or this direction, suppose I displace my finger from this point to this point, then what will happen? the normal reaction is acting here in this direction, weighted downward. So W and N, what they will do, they will form a couple. W here and N here. If you displace your finger this position to this position, so now W and N, they will form a couple. So what happens because of this couple? This will rotate in this direction. Similarly, if you displace your finger from this position, move your finger here, then couple will be formed, normal reaction in this opposite direction, and it will rotate in the opposite direction. So what happens? Why this is balanced in this position? So it means that the whole of the mass is concentrated at this point. So weight also is acting in downward direction at this point, and I am applying a force against that. So both are in same line, opposite to each other. Net force is 0. It is balanced. So what this point is called? Center of mass. Now it is clear. The point where effectively whole of the mass of the body is concentrated. That is called center of mass. So a body small particles, minute particles, each is having its own mass. So this body can be divided into very small, suppose we have this one. So it can be divided into numerous small particles, M1, M2, M3, M4 and Mn. So if I put it like this, then gravity is applying force on each particle in the downward direction. Similarly here, here, everywhere the gravity force is acting in the downward direction. Then why do we say that the mass is concentrated at one point? This is because we say that the resultant of the gravity force is acting at this point. The gravity force, if you consider the property as individual masses, composed of individual masses, then on all these masses or particles, the gravity force is acting in the downward direction, and the resultant of that force is assumed to be concentrated at one point. That point is called center of mass of the body, and we can show it. So this is the center of mass of the body. Now suppose I have this point as origin. So position vector of M1 is R1 with respect to this point, and that of M2 is R2, M3 is R3, and that of Mn is Rn. So here the force is acting at each point in the downward direction, and if we assume that this point is the center of mass of the body, the position vector of this is RCOM. So here effectively we assume, this is our assumption, that center of mass is the point where effectively whole of the mass of the body is concentrated. So if you squeeze this mass into a very small space, so that this can be confined into a very small space in place of this disk, then whole of the mass can be assumed to be kept at this point, and the weight will be acting in the downward direction, and we can balance this by applying the force. So this is the definition of center of mass. So you can define this. So point where whole of mass of body is assumed to be concentrated. This is called the center of mass. Now, center of gravity is the point where effectively the gravity force is acting on the body. Now, what is the difference? So, COG and COM are same if gravity force is uniform and parallel. Both are same. So in general, we will assume that COM and COG, they are same as far as our discussion is concerned. Now this is the first point. What is COM? Second thing is, why do we study these things? Because you know that there is a cause and effect relationship in nature. And you have studied this in thermodynamics, that whenever there is a difference of temperature, the heat flows. If heat is flowing from higher to lower temperature, it is because of temperature difference. If from low to high, then you will have to provide input, electrical energy, work. Water flows because of potential energy difference. Wind flows, why? Because of pressure difference, temperature difference. So there is a cause, there is an effect of that. Similarly here, why do we study this? Because there is a need behind everything. You all know the laws of physics. Mechanical engineering or any other engineering, you can say that it is the daughter of science, particularly physics. And the mathematics is the brother of physics. So engineering is nothing without science, particularly physics. Also you can include chemistry and mathematics. If you don't have interest and aptitude for mathematics, then physics and mathematics, particularly mathematics, then engineering is not for you. So you must have an aptitude for that. So develop it if you are going to really become a good engineer. If you have to clear good exams, if you have to find very good job, like in R&D, you have to go for IES or you have to go for IAS, etc. Or you have to study these subjects. Really a good engineer, not getting the degree and standing in the queue to find a job or going for software. I'm not against software, but if you have to be in this field, a really good one, to be remembered by the people, then you have to have a strong background and aptitude for mathematics and science for engineering. So here on this channel, I will cover the mathematics portion also for BTech for different exams, IES or GATE, etc. So friends, the reason is there are different laws of physics, like law of motion, F equal to m into a, and we have F equal to rate of change of momentum, L angular momentum. Rate of change of that is equal to the torque. Torque equal to R cross F. Then we have external torque equal to I omega. Here we are considering this as a vector. So my question is, suppose you have a body kept on the ground like a football. You are kicking it. So when you apply the force, the body is moving. Suppose the body is kept like this. A force is applied. When you apply the force in different positions, here, here and here, what will happen? Where is the center of mass? Center of mass is at this point. So when you apply the force here, so it will, what this will do? I can replace this force with a force and a torque. How? This is the force. This is the center of mass of the body. So about the center of mass, if I apply two parallel and opposite, this is F, these two are also F. So this and this, what they will do? They will create a couple, and this force will be a force in the linear direction. So what the couple is trying to do? It is trying to rotate the body. About which point? About this. And this force, which is acting at the center of mass, will try to move it in the linear direction, in the direction of force applied. So if you apply the force here, it will create rotation plus translation. If you apply the force here, the rotation will be different. This force is rotating in this direction, this in this direction. So rotation and translation for this force and this force, other than the force applied at the center of mass. When you apply the force at the COM, in that case the body is having pure translatory motion. So where do we apply these laws? The question is, where do we apply these laws? Because these laws are applicable only to the point bodies. What is the point body? You can consider that whole mass of the body can be concentrated at one point. The size of the body is very small. Okay, so we call it to be a point body, and these laws of physics or engineering are applied only to the point bodies. So we have to reduce the body for the purpose of analysis for applying these laws to a very small point where whole of the mass is confined. So that is called a point body, and that's why we find the center of mass. So here I assume that this mass of the body is m. Suppose m is confined in this space and this force is applied, and then these laws are applicable. Translation. So whether it is rotation, whether it is translation, these laws can be applied only for bodies of very small size, point bodies. And what we do here is we reduce a body to a point body for the purpose of application. We assume that the mass is concentrated at one place. That point is considered as the whole, representing whole body, point body. So this is the reason why do we study this. This is the answer to the second question. So after this, we will discuss these bodies. First, let us take the linear bodies. So first of all, before discussing the linear body, let us find the center of mass of a two-point body, not bodies. So we have these two bodies of masses m1 and m2, and they are separated by the distance, center to center distance. This is say d. Like you must have come across the problem of a binary star. Two stars which are at a certain distance from each other and having motion about a point, that point is called the center of mass. So they are rotating both about that point as a system, just like a dumbbell. You must have used a dumbbell in gym. So you can consider that two balls on the two sides of this dumbbell, if they are joined by a light rod, very light rod, which is assumed to be massless. So that is called a two-point body. So binary star is also a two-point body. And we can apply this also to a body which is having motion like this. Two bodies are connected by a spring, or one body is moving towards the other body which is having spring moving in, or this may be moving, may be stationary. In this we apply the force like this, we push or we pull. Similarly, this can be the case. So when the spring is compressed to the maximum, in that case the bodies are stationary. So we will find the center of mass, and when we discuss the simple harmonic motion, it is of utmost importance, this concept of center of mass. So we can assume that this is the center of mass of the body. So I can assume that this spring can be divided into two parts, and one body is having motion like this. M1, M2 are the masses. Total length of the spring is L. This distance is L1 from the center of mass, and that of the second one is L2. So we can consider their motions separately about the center of mass and find the frequency of the system. So this we will also be discussing during the topic of the simple harmonic motion. So here let us find the center of mass. How to do this? Its weight is m2g in downward direction and it is m1g in downward direction. Now this distance d is large enough as compared to their radii. Suppose the center of mass is at this point and this is the vertical to the center of the mass. So the distance of center of mass from their centers, this is suppose R1 and this is R2. So this point is considered to be the point where effectively the mass is concentrated. So if I take any force or torque passing through this, that must be equal to 0. So sigma of the moment about this point is equal to 0. So what are the moments? What is the force which is creating a moment about this point? This weight and this weight. This is rotating in this direction. This in this direction with respect to this point. So I can write one direction. Look, let us this be positive. This be negative. M1g minus M2g. Multiplied by the distance d1 is equal to 0. So M1 d1 is M2 d2. And I have written this d1, sorry, this is R1. And R1 plus R2 is equal to D. Now we can solve this, putting the value of R2 here. So R1 plus M1 R1 by M2 is equal to D. So this gives us R1 is M2D upon M1 plus M2 and R2 is M1D upon M1 plus M2. So this is how we find the center of mass position for the two bodies. Now one thing is important here that it is near to the heavier body. Is always near to the heavier body. How this happens, let me explain. This is a lamina. This is a circular plate. Where is the center of mass located? At this point. If I show you the side view or front view of this is the top view. This is the plate. Center of mass is at this point, passing through the axis, passing through the center of mass. So the weight is acting in downward direction. This is the C wave. Now what I do is I am making a through hole into this. I am cutting this portion out. So this portion is removed. So where is the center of mass located now? Mass is removed from this side, so mass is concentrated on this side. If you want to balance it by applying the force, you have to apply the force in this direction where the mass is shifted. So mass is shifted on this side, so somewhere here you will find a new center of mass. So center of mass is always shifted towards the heavier mass. It is always located towards the heavier mass. This is about the introduction part of the center of the mass. Let us now discuss the position of center of mass of some bodies. Let us first discuss the discrete bodies. So the question is, we are having these bodies of different masses that are kept at the corners of a square. And we have to find the position of center of mass. Now these bodies are not joined, that's why they are called discrete. If the masses would have been same, then where would have been the center of mass located? At the geometric center, where the diagonals cross each other in case of same masses. At this point. But here they are not joined and masses are different. So now we have to find the position of center of mass of the body, and you must remember what is the formula for finding the center of mass. The position of vector of center of mass where Mi is the ith particle, as I discussed in the beginning, and Ri is the position vector of that particle with respect to a fixed point in the space, which may be inside the body, may be outside the body, and that is called the origin. Sometimes also known as pole, because every vector has to be located or specified with respect to a fixed point, that is called origin or pole. That is just like you are flying a kite, and the kite is flying because you are holding the string in your hand. So your hand acts like a pole or a fixed point position, and the string, if it is straight enough, because that does not remain straight, but assume it to be a straight line, and then that is, it can be assumed that it is a vector, position vector. And where it is, which points it is joining? From pole to the center of mass of the kite. This is just an assumption. So R can be written as equal to 3 coordinates in space, x, c, I plus y, j plus z, k. So this is the COM, this is the origin, and this point is having the coordinates x, y, z. Now we have to decide that pole or origin. Suppose I take this point as origin pole, A, B, C. You can take in any order. Like the size of this is A, this is also A. So this is taken as origin. This is, the coordinates are specified as positive x and y. A0, 0, A, A. Sorry, this is A, this is 0, A. Now apply this formula. The center of mass, in this case we have to find x and y coordinate, because this is not a solid body, so z is not necessary. So x, COM in this case, M1. This is 1, 2, 3, 4. You can take any order. You can take this 0, 0 anywhere, this, or at the center or at any other point which you can specify. But the answer will be with respect to that point only. Suppose I say that center of mass occurs at this point. So if you select origin as any other point, then distance of this point from that will change. That will be specified with respect to this point only, that origin only. But the point will remain fixed here. Its center of mass, it does not mean that if you select the origin here, center of mass is shift here. It will remain here. So XCOM is M1, 4M into 0. Its X coordinate plus M2, I'm taking this as 2, you can take any order, 3M into A plus 2M into A plus this is M into X coordinate is 0 divided by total mass. Zero, 3 MA, 3 to 5, so 5 A divided by 10 or A by 2. Now let us find Y. So M1, Y1, 0. M2, the order should not change. Total mass is 10. Sum of these. So 3A by 10. So the center of mass lies at X coordinate is A by 2 here at its center. Allow this. Y is 3 by 10, 0.3. So this is A, so this is half, this is 0.3. So the COM coordinates are A by 2, 3A by 10. This is the point where center of mass is located. So as I told you that if you change this position, origin, take here, this point will remain same. But then these coordinates will be measured with respect to this point. So this is how you can find the center of mass of a discrete body. Now let us discuss some bodies like the one which is linear. Suppose we have a solid rod. If the mass density, that is mass per unit length, in case of one-dimensional bodies, so here we assume that diameter is quite small as compared to length. Then we can assume this to be one-dimensional. If it is having constant mass density, in that case, COM is at its geometric center. But its mass density is variable. Let us assume that its mass density is variable. So it is kept here. Let us take this point as origin, x-axis, y-axis. So it is symmetrical about x-axis. Its center of mass will be varying only in x direction and not in y or z direction. The mass density of this mass per unit length. This is variable, varies along the length. Suppose this is, now this is, I have written this as lambda. In case of the linear bodies, mass density is represented by lambda m by L. In case of planar bodies, rho mass per unit area. In case of solid bodies, sigma mass per unit volume. So these are invariably used. These symbols, they can be, sometimes you will find mixed, so it does not matter whether I write lambda or rho for this. It is mass per unit length. It is given by, suppose, ax square. Now I have to find the position of center of mass. So see, this is symmetrical about x-axis, not about y or z. So only x coordinate of center of mass is to be calculated. So I will take a small element of this, which is at a distance x from the origin and having a thickness dx. Now this is the element, and you have to find the center of mass of this, assuming this to be a continuous body, no voids, etc. So x com integral x dm. Dm is its mass of this small element, m is mass of entire body, and x is the distance from its center of mass divided by integral of dm. So what is dm here? Dm is mass of this element. This is lambda. Lambda is the mass density. So lambda into its length dx. So ax square dx. Here a is a constant. So x com is x into ax square dx divided by integral ax square dx. If mass density is not uniform, then you will write this under the sign of integration. Otherwise, here I can write the total mass like this. If it is not constant. If it is constant, I can write this integral of dm, and integral of dm is equal to m, the total mass, if it is constant. If lambda is constant, I can write it like this. So x is the variable. Here I can take x equal to 0 and here x equal to l. From 0 to l. So a x cube x4 by 4 0 to l divided by a x3 by 3. This is 3 by 4 L. It means the center of mass is located at this point. This is 3L by 4 from this origin. Here we have the center of mass of this rod. This is how you can find the position of center of mass of a body, linear body, which is having mass density. Now after this, let us discuss how to find the position of center of mass of a wire which has been bent in the form of a circle, semicircle, semicircle, arc, etc. So a wire of constant, you can assume that bent in the form of 1/4 of a circle. This is the center, and you have to find the position of center of mass. So there are several ways of finding this, and this depends upon the coordinate selected. You can select the polar coordinate r theta. You can select the xy coordinate system also. And you also must be knowing that for the solid bodies like a cylinder or the symmetrical, which have cylindrical symmetry, r theta z coordinate system is selected cylindrical. For solid bodies like a shell, etc., or a hemisphere, etc., then I mean hemispherical shell or a shell or a hemisphere solid, we select the r theta phi coordinate system. Or in case of general bodies, linear bodies, xyz coordinate system, and in the disk, etc., you can select any coordinate system. You can find it by xyz also, x or y. The Cartesian coordinate system can be converted into this polar coordinate system, and both can be used. So here we have to find the center of mass of this. Its mass is assumed to be m, and mass density is uniform. So first of all, let us find this by using the xy coordinate system. Suppose this is the x-axis and this is y-axis. So this is our origin. Let us take a small element of this. This is the small element. This and length of this, suppose this is dl. dl is the length of this small element and the wire which has been bent in the form of one quadrant of a circle. The mass density is assumed to be uniform. Now the center of mass, suppose it is at this point. So its coordinates are xc, yc. This is the x coordinate. This is the y coordinate, xc, yc, with respect to this point. These are the coordinates of center of mass of this. So similarly, okay, now I can write what is xc. Integral x dl, mass is varying along the length only, along integral of dl. Mass density is constant, so x into dm means dl into lambda, So dl into lambda is equal to d. So this is constant. So then you can write the sign of integration and can cancel this. This is symmetrical. This body is symmetrical about this line. Means about both x and y axis, this angle is 45 degree. So we need to find both xc and yc. Similarly, yc, ydl upon dl. Now it is clear that why I have written dl in place of dm. Suppose this distance this is dx and this is dy. If I show it separately, this is the very small element. The length of this is dl. So this is the x-axis, this distance is dx, this is y-axis, along this it is dy. This is the point where the center of mass of this small element is located. So I can write from this is the right angle, dx whole square plus dy whole square equal to dl whole square. And r is the radius of the wire, suppose. So equation of this circle is x square plus y square equal to r square. If you differentiate both sides, 2x dx plus 2y dy, r is a constant, is 0. So x dx is equal to minus y dy. this relation we can use to correlate dx and dy. So I can write that dl is from this under root of dx whole square plus put the value of dy from here upon y. So x square plus y square is under root r. So dl is r upon y into dx using this. So now we can find the x and y coordinate system. Sorry, the x and y coordinate of center of mass. So yc y dl by integral of dl. Now you can put the value of dl. So y into r by y dx by integral r by y dx. What is the variable here? X is the variable varying from 0 to r. So y cancels out. R is a constant, can be taken outside and it can be cancelled. So what is the total length? Now here, this you should remember. Here I need not put this value because the mass density is constant per unit length. So what I have to do here is total length integral of dl of this is 2 pi r divided by 4. Pi r divided by 2. This is the length and integral dl is total length 2 pi r. If the mass density would not have been constant, then I would have to put this as I did previously here. So put this pi r divided by 2. So r will be cancelled, can be taken outside, and you will get this is 2r divided by 5. So this is symmetrical, x and y are same. So xc you can find same way, you will get 2r by pi. So here somewhere at a distance 2r by pi from here, 2r by pi from here, you have its center of mass. This is the one method of finding the center of mass. Let us do it by another method also. Taking the same element of length dl, we will be using here the polar coordinates. This is subtending an angle d theta at the center. And this angle is say theta. Considering this small element a, b. This distance is radius r. So b to this, if I draw a perpendicular here, this point is m. Then this is equal to r sin theta. And this distance is r cos theta. So if you consider the center of mass somewhere here, this distance, this is x coordinate, this is y coordinate. Now this distance, this to this is very small. Means what is this distance here to here? R sin theta plus half of this length. dl by 2 sin theta half, something like that. dl is very small, can be neglected. So this coordinate and this coordinate vertically and horizontally can be assumed to be same. So what is the length of this small element dl? dl is r d theta. So again, using this, yc is integral of y dl, y integral of dl, and similarly you will write xc in the same way. Here x and y are variable. Now I will write x and y and dl values here in this equation. So what is x, what is y? The distance of the center of mass point of this small element from origin, x and y. So y here is r sin theta into r d theta divided by integral of r d theta. dl is r d theta. So let us put here r d theta. Now here I have put r d theta and not equal to pi r divided by 2. What is variable? Theta is variable. 0 to pi by 2. 0 to pi by 2. Maximum value is pi by 2. So r can be taken out, will be cancelled. So r integral sin theta d theta divided by integral d theta 0 to pi by 2. So this is equal to minus cos theta divided by theta, so which is minus r cos pi by 2, 0 minus 1 divided by pi by 2 minus 0. So yc is 2r by 5. Similarly, you can find the x coordinate in that in place of r sin theta, you will be using r cos theta. Zero to pi by 2, 0 to pi by 2. So you will find that this is also equal to 2r by 5. So this is how you can find the position of center of mass of a wire which has been bent in the form of one quadrant of a circle. Similarly, we can find the position of center of mass of a wire which has been bent in the form of a semicircle. Let us do that also. This is a wire of constant mass density, bent in the form of semicircle. This is the center of the arc. Let us take a small element of this. Subtending an angle d theta at the center. This angle is theta. The length is r d theta. R is the radius. So this is a symmetrical body about the y-axis. So its center of mass will not be varying along x-axis. This is the x-axis and this is y-axis. It will be varying only about y-axis, not varying about the x-axis. So we will use the same formula, and mass density, its mass is m. So mass density is m by pi r. dm is the mass of the small element, r d theta multiplied by lambda, m by pi r into r d theta. This is the mass of this small element, and this is a continuous body. So integral dm will be equal to the total mass m of this body. So we need to find only the y coordinate. So now we will put the values in this. What is y? This is the distance of, if you assume that center of mass of this is at the center of this small element. So this point can be taken here. So this is theta, and half of this angle will be d theta by 2. So d theta is so small that theta plus d theta by 2 is approximately equal to theta, and this distance is r sin theta. So y can be taken equal to r sin theta, x is r cos theta. So r sin theta, and dm is r d theta multiplied by mass density divided by integral of dm, that is equal to the total mass. And theta here is varying from 0 to pi. So YCOM here is, this r can be taken outside, lambda can be taken outside, putting the value of lambda m by pi r into r square sin theta d theta divided by m. Theta is 0 to pi. M is cancelled, r is cancelled. So r divided by pi, integral of sin theta is minus cos theta, 0 to pi. So you can find by putting the limits, cos pi is minus 1 and 2r by pi. So the value is 2r by pi, but variation is only along y-axis. 2 by 3.14 means 0.6, around 0.6 approximately. So 0.6 r around. So this is r, 0.5 around here. 2r by pi. From this is the center of mass of this. You can assume that if a force is applied at this point, then it can be assumed that this is applied to the whole body, because whole of the mass of this is concentrated here. And then you can apply F equal to m into A. So COM is varying only about y-axis because this body is symmetrical about y-axis. So this result is very important because by using this result, we will be finding the moment of center of mass of a semicircular disk. When we move on to the continuous bodies, that is the lamina, two-dimensional bodies, in next discussion. So this is all for today. Thank you very much. Have a nice day.